According to binomial theorem, 1 plus x raised to the power n is equals to nc0 plus nc1 times x plus nc2 times x square and so on up to ncn times x raised to the power n. And this works for all n belongs to natural numbers. Here nc1 is n, nc2 is n times n minus 1 over 2 factorial, nc3 is n times n minus 1 times n minus 2 over 3 factorial, and so on. For example, if we want to find 1 plus x whole cube, then put 3 in place of n and we get 1 plus 3x plus 3x square plus x cube. But this formula works for all real values of n also. Suppose we put n equals to 1 by 2, then 1 plus x raised to the power 1 by 2 is equals to 1 plus 1 by 2 times x. And in this way, if we put 1 by 2 in place of n everywhere, then also this formula works. But the series doesn't stop after n or n plus 1 terms, it goes up to infinite terms. Okay, and this is working even when 1 by 2 does not belongs to natural numbers, right? So why this formula is working? Let us see why this is working. So first thought which comes to our mind is that we can prove this formula using an expansion like Taylor series. And here we will consider that n is a real number. Okay, so what we can do, let us suppose that 1 plus x raised to the power n equals to a0 plus a1x plus a2x square and so on up to infinite terms, and then put 0 both sides. So what we get a0 equals to 1, right? Now differentiate this equation number 1 with respect to x both sides. Okay, so what we get n times 1 plus x to the power n minus 1 is equals to the differentiation of a0 is 0, means constant, differentiation of a constant is 0, differentiation of a1 times x, that is differentiation of x is 1, and differentiation of x square is 2x, differentiation of x cube is 3x square, and in this way we can differentiate all the terms and we get new series on the right hand side. Now again put x equals to 0 on both the sides, we get n equals to a1, right? So what we get the value of a1 also, right? Now what we can do, we can again differentiate this with respect to x both sides. So what we get, we have n times n minus 1 times 1 plus x raised to the power n minus 2 equals to, now again differentiation of a1 is 0 and differentiation of x is 1, so we get 2a2 plus 3 multiplied by 2 a3 times x and so on. And again if we put x equals to 0 on both sides, so what we get a2 equals to n minus 1 upon 2, and we can also write it 2 factorial, right? So if we proceed in this way, then finally we will get that ak, that's coefficient of x raised to the power k in the series is n times n minus 1 and so on up to n minus k minus 1 over k factorial. So it seems that we have proved the formula, but here is the catch. From where this differentiation of x raised to the power n comes? Let us see. We know that differentiation of any function fx can be found by this first principle, that is limit h tending to 0 fx plus h minus fx over h. So if we have fx equals to x raised to the power n, we can say that fx plus h is equals to x plus h raised to the power n, right? So we get this expansion over this relation over here, right? So if we continue to solve this, we can take x from x raised to the power n common. How we have taken common? We can take x common from x plus h, so we get 1 plus h over x whole power n, which is equals to x power n times 1 plus h by x raised to the power n, right? So we have taken this common, and now what we can do, just apply this expansion, and then we can see that 1 and 1 gets cancelled out, and here we can take h common from each of the term, and one of the h will cancel out, and each term will have a h except this first one. So we will get x time x raised to the power n times n by x, right, which is equals to n x to the power n minus 1, like this. Okay, right? So it looks like we have proved the formula, but what we have done over here, we are already using this expansion in proving the differentiation of x raised to the power n, right? So what we are doing, we are basically proving this series expansion with the help of differentiation, and we have proved this differentiation with the help of this series expansion. We are proving both of these with the help of each other. So we are getting some information out of nowhere. So what we need to do? We need to prove one of the following without using other. Either we have to prove that this series is working for all real numbers, or we can prove that this differentiation works for all real number. Okay, we should note that both of these are working for n belongs to natural numbers, right? We know that both of these are working for n belongs to natural number. Okay, still that is what we know. So let us start with the easy one. Let us prove that this differentiation is working for all n belongs to real numbers. And for this, let us start. Let's take a start with proving it from positive rational numbers. Okay, so we will prove it for positive rational numbers, and after that we will extend it to all rational numbers and then to real numbers. So let us suppose that n is equals to p by q, because all rational numbers can be written in the form of p by q, and since we are taking positive rational numbers, so let us assume that p and q belongs to natural numbers. Okay, now put p by q in place of n, and on both sides take this raise both sides to the power q. Raise both sides to the power q. So what we get? We get 1 plus x raised to the power p equals to 1 plus a1x plus a2x square, and so on, raised to the power q. And on putting x equals to 0 both the sides, we get a0 equals to 1. Now since we know that p and q are natural numbers, therefore our differentiation will work over here, right? So what we get? We get p times 1 plus x raised to the power p minus 1 equals to q times this series to the power q minus 1. And then according to chain rule, we have to do the differentiation of this series again, and we have to take it in multiplication. So we get a1 plus 2a2x plus 3a3x square, and so on, right? Now what we can do, we can put x equals to 0 on both the sides, and we get a1 equals to p by q. Now you might be thinking that we have to again differentiate it, and then we have to find the value of a2, but we will not do that tedious thing. Okay, we are just stopping over here, and we will again come to the differentiation to prove the differentiation. Okay, so here we get that this formula is now working for n belongs to positive rational numbers, and we have come up with these first two terms. We have find something for these first two terms. Okay, for a0 and a1, and remaining terms are still uncalculated, you can say. These are not calculated. Okay, so now let us again try to prove this differentiation, and here we can see that without using these a2 a3 and so on, we can come up to the result nx raised to the power n minus 1. And so this formula is true for all positive numbers, all positive rational numbers. Now let us now to extend it, we will extend it to the, I mean, for negative rational numbers later. And this was something which was quite straightforward, and straightforward things are boring, right? So let us try something interesting. So let us suppose, let's again start with the same series, and after first time differentiating, let's try something different. Here, let us write this 1 plus x raised to the power p minus 1 as 1 plus x raised to the power p over 1 plus x. And in similar way, here q minus 1, here adjust this q minus 1 as series to the power q over this series. Okay. Now since from here we know that 1 plus x raised to the power p is equals to the series times q. So in place of this, in place of this series, we can again put this 1 plus x raised to the power p, right? Now 1 plus x raised to the power p gets cancelled out from both the sides, and now we can this transfer this 1 plus x over here for multiplication, and this series here for multiplication, right? So what we get, we get p, we get this series a0 plus a1x plus a2x square and so on equals to q by p times 1 plus x times a1 plus a2x and so on. Okay, now let us multiply these two brackets together. So when we multiply a1 with all these, we get this series as it is over here, right? Okay, now when we multiply x with a1, we get a1x. When we multiply x with this 2a2, we get 2a2x square, and in this way we get other terms. So here we have q plus p times this bracket written over here. Now let us compare the coefficients. Suppose if we have to compare the coefficient of x cube, so what we can write, we can write a3 equals to, now here there must be a term 2a3 with the x cube, right? Here there will be a 3a3, I'm sorry, 3a3 times x cube, and here 4a4 times x cube must be present over there, right? So what we can write, a3 equals to 3a3, more precisely q by p times 3a3 plus 4a4. Okay, in this way we can compare all the coefficients. So we get ak equals to q by p times k plus k plus 1 times ak plus 1. Now on rearranging the terms, we get ak plus 1 equals to p by q minus k over k plus 1 times ak. So here we get a recurrence relation with the coefficients of the series. Now we can write here ak, if we write k in place of k plus 1, then what we get p by q minus, in place of k we will get k minus 1, in place of k plus 1 we get k, and like this. So we can put this value of ak in this ak again. So what we have, we get ak plus 1 equals to p minus k times p by q minus k minus 1 and so on, right? Times ak minus 1, and again we can put the value of ak minus 1, and in this way we can continue up to a1. And since we know that p by q is equals to n, and this is also equals to this was also equals to a1, and therefore ak plus 1 is equals to the required coefficient. This was what we were trying to prove, right? This is the coefficient which is present in the series which we are trying to prove. Okay, and this we have proved for positive rational numbers. Still we need to extend it to negative rational numbers, right? So to prove it for negative rational numbers, there is a hint for you. We know that d by dx of x to the power minus p is equals to d by dx of 1 upon x raised to the power p. And now using the chain rule, you can continue. So you can prove it for negative rational numbers by yourself. Okay, nice. Now what we have this series expansion proved for all rational numbers. Now we have to extend it to real numbers, right? So if here x is greater than 0, then 1 plus x is also greater than 0, right? I mean 1 plus x is greater than 1, right? And if so let us take example. Suppose we have 2, and if we ask that 2 raised to the power 100 and 2 raised to the power 101 or 100.1, which one is greater? So the greater power will be greater, right? The side with the greater power will be greater. Why? Because the bases, both the bases are greater than 1, and things just work opposite sign with bases less than 1 greater than 0. Okay, so here we can write 1 plus x raised to the power n minus 1 is less than 1 plus x raised to the power n2. Now for all the irrational numbers, we can find n1 and n2 tending to n, such that n1 is less than n and n2 is less than n2. For example, suppose we have under root 2 equals to 1.414, or let us take the example of pi 3.14. Can I have a large container of coffee? And in this way, I mean, actually I remember these more places, that's why I have taken the example of pi. So we can find many irrational numbers very much close to the pi, and in this way you can find many irrational numbers which are tending to pi. Suppose 3.1 is less than pi, and pi is between 3.1 and 3.2. 3.14 is less than pi, and 3.15 is greater than pi, right? 3.14159 is less than pi, and 3.14159 is greater than pi. So we can just get close and close and close to the pi. So it means this formula is working on both the hand sides of pi and very near to pi, means the limit is existing. And also, since 1 plus x raised to the power n must be continuous with this fact, we can say that its value on the pi must also be equal to the series or the limit which we will find on both the hand sides. So since for all real numbers we can do this, that's why this formula is working for all real numbers also, right? So finally we can say that this series expansion works for all n and x belongs to real numbers and x greater than -1. Okay, don't forget to like and share our video, and for more such videos subscribe to our channel Brain Exploders. Thanks for watching.